Ah, d'accord, okay. Okay, so I've been struggling to decide. We have one lecture left. This is our last lecture. Um, and we have the material for 2 lectures left. So I've been struggling to decide whether I should talk about the response of the hydrological cycle to climate change. And mainly, I would say the uncertainty is in the extremes, or that's mainly what I'll talk about. Still, again, this is still at the stage of research. And should I talk about clouds and climate? And there have been a lot of questions from you about climate change and the issues that arise. So I couldn't decide, so I've decided to give you a quick overview of both. I mean, quick, more than half an hour, but still. There's a lot to say about those 2 aspects. And whatever I skip, I'll give you the references, so you can go and check the literature yourself. Okay, so here's the double lecture. First, precipitation extremes. I'll mainly talk about the tropics. And the reason is that, as we've seen in this image of water vapor, in the tropics the clouds have small scales. And as you know, climate models have resolutions of few hundreds of kilometers right now. And even if they improve their resolution, the clouds will still be either not resolved or marginally resolved. So that means that all the processes in the tropics are very hard to resolve for those models, and they have to be parameterized. And a lot of errors comes from convective parameterizations. In the exotropics, we saw that the clouds were embedded within larger scale structures, and so it's not surprising that the models have an easier time dealing with those clouds. It's still not perfect, but it's not relying on a convective parameterization as much. So for the mean precipitation change, so the question I want to address is how will precipitation change with climate change? Okay, so I'll start talking about the mean precipitation. So the distribution of mean precipitation, the climatology is shown here. And this is something that we understand quite well because it basically comes from thermodynamics, from the Clausius-Clapeyron equation we saw. So I want to go through this. So this is the climatology. This is a multimodal mean. And you see that there's a maximum precipitation in the tropics, some in the exotropics, and unsurprisingly, in the subtropics, where the Hadley cell is descending, there's a minimum here and here. Now, if you look at the change as projected with climate models, and they agree on this, I should say, so this is what we call a robust result. The models agree, and we understand it from first principles. The precipitation increases in the tropics, so where it's the strongest. It also increases in the exotropics, where we had this weaker second maximum. And it decreases in the subtropics, where it was already weak. And so the picture that emerges is a strengthening of the precipitation patterns. And there's a very famous paper by Isaac, who'll be here at the summer school, and Brian Soden. It's called The Robust Response of, I forgot exactly. If you Google robust response held, you'll find it. And it has that was, I think, last year that I counted the number of citations. It might have gone up. It has a huge number of citations. It's a seminal paper in our field. I highly recommend it. And Isaac will be here, so you can discuss with him about this paper. But so it's something that we understand, and the reason why it has to be that way is because we've seen that atmospheric water vapor, if the changes in relative humidity are not too large, which the models tend to indicate, they're not zero, but they're not too large, and surely they're smaller than the increase in the saturation humidity, which follows the Clausius-Clapeyron. And if you remember, it was almost exponential. Okay, the saturation water vapor increases roughly exponentially with temperature. Roughly because there was a 1 over t squared factor, but it's roughly exponential. And so what that means is that if the relative humidity doesn't change too much, then the atmospheric humidity will follow the saturation one, so it will increase very strongly with temperature. So now assume that the dynamics don't change too much. What dictates the fact that there's precipitation here? Someone noted that this is not exactly the same as the distribution of water vapor, and that's because you need condensation to have precipitation or clouds. And in order to have condensation, you need upward motion, or you need convergence. Okay, so the reason why there's precipitation is because there's convergence. And if they converges, the dynamics do not change. the amount of precipitation that you get, the amount of convergence of humidity will increase following Clausius-Clapeyron. Okay, and similarly, the divergence here, if it doesn't change, the amount of divergence of water vapor that you get will increase or decrease negatively following Clausius-Clapeyron. Okay, and similarly here. So you would expect the pattern to strengthen, and this is what you observe. Okay, so that's for the mean. The models agree. The problem is when you start looking at precipitation extremes. This is a paper from about 10 years ago looking at precipitation extremes. So this is the 95th percentile of precipitation at each latitude for various models. So this is the value. Yeah. Ah, yeah, good question. Yes, I think it's daily precipitation. Yeah, yeah. But there have been other studies looking at this, and there's now wider range of studies. Tapio has worked on this that show that the extreme values of precipitation, the strongest precipitation, do not agree between different models. And so the 95th percentile is the value of precipitation that you only reach 5% of the time. Okay, so 95% of the time, the precipitation will be below this value, 5% it will be above. So it's an indicator of high precipitation values. And so in the tropics, as you can see, they are all over the place, and it's not correlated with the resolution. You might expect that with a finer resolution, you'd get higher values for a given percentile, but it's not correlated with the resolution. In the mid-latitude, it's better, as you would expect, because the features are larger and easier to resolve for the climate models. So this was kind of a puzzling paper. There was another puzzling paper which raised a lot of attention by Bjorn Stevens and Sandrine Bonny in Science, where they showed the response from 4 climate models run in idealized simulations, so aquaplanet, no land. When you run climate models in idealized simulations, you really let the physics express themselves. So you would expect more variability than when you have land, which forces some of the features that you're looking at. But still, you would not expect such a wide range of response. So here, this is the change in precipitation and in the cloud radiative effect. So are the clouds cooling or warming? And I'll be more precise about this later. But basically, it's whether clouds are warming or cooling. This is the change in response to an increase in SST of 4 degrees, uniform over the planet. So it's a very simple idealized thought experiment. And as you can see, the models, in the exotropics at least, they agree pretty much for precipitation. And here, at least on the sign, to a certain degree, they agree. But in the deep tropics, they don't. And they don't even agree on the sign. So that's embarrassing. And there is another nice, almost philosophical piece by Isaac in Science saying that we need a hierarchy of models to understand these processes. And I don't think I have to convince this crowd, because you're all very aware that we need simple models to understand the complex models. Okay, and so the simple model I'll be using today is the same one we discussed last time. And now it is fully described. And this is the paper where you have the equations in the appendix. So it solves the inelastic momentum, continuity, and scalar conservation equations. The radiative cooling is interactive, like last time. The sea surface temperature is fixed to various values. We'll do warming experiments where we change the SST. The domain is still squared and doubly periodic. And there's no rotation, again, to simplify things. We're in the deep tropics, so the Coriolis parameter is small. So I'm happily neglecting it. And then we run to statistical radiative convective equilibrium. Okay, so the way the model works, you have an intermediate regime where the equilibrium is not reached, and then you start your analysis once you have reached equilibrium. The equilibrium means that on average, if you remember, on average over the domain, the radiative cooling of the atmosphere is balanced by the latent heating, by the precipitation, and the sensible heat flux, but it tends to be small. Okay, so on average, the radiative cooling is equal to the mean precipitation. And I added this following yesterday's lecture, something I should have mentioned I didn't when I showed those simulations. There's a sponge layer, and it's typical of those types of simulations. There's a sponge layer above here, so I'm not showing you the sponge layer because it's not physical. But the point is to absorb those gravity waves that you heard about yesterday. Classical trick to get rid of most of the waves. Okay, so precipitation extremes, what do we expect? Well, let's start. So we saw we can't use climate models to know how precipitation extremes respond to warming. So what do we have left? We have theory, we have observations, and we have high-resolution simulations, to have hints at least. I won't talk about observations because I had to fit 2 lectures into one, so I removed it, but if you're interested, please come talk to me. Let's talk about the theory. If we said if the dynamics don't change too much, you would expect that the precipitation extremes should follow the amount of the excess water that you have or the increased water that you have in your convection. And we saw that the moisture increases following Clausius-Clapeyron. So maybe the first idea that was actually put in the literature is that the precipitation extremes should scale with Clausius-Clapeyron. So in terms of number, what does that mean? Stabio gave you the global mean value of Clausius-Clapeyron, the increase in humidity, but it actually varies with latitude, and this is, as a function of latitude, the % increase per Kelvin of different humidity fields. So the water vapor is in red, and in the deep tropics it's more than 8% per Kelvin. As you would expect, you have a larger increase in the tropics, smaller in the subtropics, and it increases again at mid-latitudes. Okay, I won't talk about the other curves now. And here are the questions that I want to specifically target here. By how much do precipitation extremes increase with warming? And how does it compare to this theoretical expectation of Clausius-Clapeyron, so to the change in water vapor? And then do the dynamics change or not? And if they do, how does that impact precipitation extremes? And then can we derive a simple relationship between the extremes and the larger mean quantities? And we'll first do this in the simplest case, the disorganized popcorn convection. And then we're going to see whether convective organization may play a role in that. Okay, so the cloud resolving model, I've described it. Now, I just want to describe the specific experiments that we'll be doing here. Actually, for this case, I will impose the radiative cooling profile. And the reason is, first, it makes the picture simpler, and when things are complicated, you always want to simplify. But another reason is that, as I told you, it's a model which is in radiative convective equilibrium. So the mean precipitation over all my domain, or the mean evaporation, they are equal. The mean precipitation has to balance the radiative cooling. And so by fixing the radiative cooling, I control the amount of mean precipitation change. And what I want is to see the actual change in precipitation extremes, not due to the change in the mean. Okay, so I'm controlling the change in the mean. That's a detail, but I just wanted to mention it. Might go a little fast, but yes, yeah. You get the change in the mean that you put in, yeah. Yes, and another thing so I changed not so much the value, doesn't change very much the way I put it, but I do have to stretch the profile vertically. And the reason is, with warming, the whole atmospheric profiles tend to stretch vertically. And so if I warmed the SST without letting the radiative cooling profile extending accordingly, I would get very weird things, like you get weird clouds. And so you have to be consistent, so I do have to change. I cannot use the same radiative profile, but I simply stretch it. And then the mean is what you'd expect. It's very small, the change in the mean. So that is a way to control this. Yes? Yes. Yeah. I can show you. I think I removed them, but I have a lot of the extra slides at the end. I started from 100 slides, and I think we only have less than 100. But I do have it at the end if you want. I can show you. You might have, I forgot how much exactly, but it's smaller. It's smaller than the two. It's 1-2%. It's this order, perhaps. Yeah, I forgot. I have to check, but yeah, it doesn't change the extreme. I've played with it. It doesn't matter for the extremes. That's the key thing I wanted to make sure. Yeah. Oh, that's a good question. I didn't tell you about the resolution. Oh, it's here. I forgot. Thank you. Yeah, yeah. So here, this is a simulation that I did for aesthetic reasons. I've never actually used it for research beyond just looking at it to get intuition. The actual simulation here, we wanted to have some mesoscale to allow maybe for some mesoscale. We didn't have to force it. We didn't want to force it, but we wanted to allow some mesoscale circulation. So we chose to have a big domain and a resolution which is therefore quite coarse, 4 kilometers. And I'll come back to that. There's another study that took the other extreme, and we find the same thing, so that's reassuring. For the temporal, the time step is 10 seconds. And then for the extremes, I'll both look at daily precipitation and hourly precipitation. And the point is they give the same result. So we'll check that. Yeah. Thank you. I was going to forget that. Okay, so first of all, what do extremes look like? Well, if you remember the life cycle of the thunderstorm, we would expect, basically, when would you expect the strongest precipitation? Would it be at the beginning or at the end? At the end, right, when you have the downdrafts and the cold pools. So we expect to see something like this, where you have still upward motion here, and down, it's hard because it's moving, but downward motion below, right? Something like a plus and a minus, with strong precipitation and downdrafts below, and maybe some upward motion at the edge of the cold pools. We mentioned that. Let's see what it looks like. Something I didn't mention too, we've added some shear just so that it would be a little more realistic, because in real life you do have some background wind, but it's weak. And so here I'm showing composites in the direction across the shear and in the direction along the shear. Along the wind, sorry, I should say. It's not along the shear, it's along the wind. And this is clouds, vertical velocity, and precipitation. And by definition of the composite, basically what I do is I take all the points where precipitation exceeds, whatever we say, 700 millimeters per day. I take a snapshot, and then I average all those snapshots around the extremes. So it doesn't mean that each individual event looks like this, but this is this gives you an idea of the typical conditions that lead to that. Okay. So the condensate, we do see that there's a high cloud and not much cloud here. And if you look at vertical velocity, you do get the downdrafts that we were expecting. Interestingly, actually, you do see the updrafts and the cloudiness at the edge of the cold pools. And obviously, the precipitation is maximum here because that's how I compute the composites. And just to mention, because we've seen this, with shear, there's an asymmetry. And as you would expect, the favored upward motion is the upwind. If you check the vorticity, this is where it should be. Okay, so that's to give you some idea of what it looks like. Now, what's the value of this precipitation extreme as a function of percentile? So what's the 95th percentile? What's the 99th percentile in the cold run? And how do those values change when you make the model warmer? Okay, so this is what you get, and I will walk you through this because it's early and you had a lot of lectures. So this is the value of precipitation in the cold run. By cold, I mean 300 Ks, right? I have the tropics in mind. And here, this is the value of the precipitation extremes in the warm simulation. And the value is shown here in millimeters per day. And this is the value as a function of percentile. And so what I'm interested in is the difference between these red and blue curves. And so here I'm showing the ratio. Okay, so what does that mean? Let me just give you an example. Let's pick our favorite 95th percentile. So again, it's the value that's only exceeded 5% of the time. It's quite an extreme precip. So if we look in the cold run, we get something like 17 millimeters per day. If we look at the warm run, it's 21 millimeters per day. And so you can do the math. That's a 23% increase, and that's what I report here, 23%. So 1.23, because I didn't make it a percent. It's just the ratio. Does that make sense? Yeah. Okay, so what do we see? There are several things. First of all, it's above 1 everywhere. So the extremes increase. The extremes increase, regardless of the percentile. So we do indeed expect an increase in precipitation extremes with warming, at least according to this idealized simulation. And then if you look at the highest percentiles, they somewhat asymptote to something. Yeah? And this is true of daily mean precipitation, and the surprising thing is that it's true also for hourly mean precipitation. And obviously, if you look at the actual values, the hourly values are larger, because when you do the daily values, you tend to smooth things. So the values are different, but the amplification with the warming is pretty much the same, around 7% per Kelvin. Okay, so why, obviously the question is why 7%? So let's go back to the equations, and I'll give you the exact equations from the model. Here, this is the dry static energy equation, in terms which we didn't have before, and I'll explain what they are a little below. It will be easier to see what they mean. But you do have a contribution from liquid and solid condensates, the rate of change of those quantities. And then you have obviously the latent heat, which enters the dry static energy equation. And I've omitted a term here. You've seen the dry static energy equation at least 5 or 6 times. So what's missing? Radiation, the radiative cooling. Yeah, it's written above. So I've neglected the radiative cooling. Why? No, actually, it still enters. It still enters. It's not because it's radiative convective equilibrium. Yes, I have it written. Some people haven't read it. Yeah, it's because I'm interested in precipitation extremes. And so in the places where the precipitation is very strong, you can imagine that the radiative cooling is completely negligible compared to the latent heat. Looking at places where the latent heat is the largest, so I don't have to worry about radiative cooling, and in fact I don't have to worry about horizontal advection because again I'm in those deep updrafts. So all I have to worry about is the vertical advection. And then because I'm in the updrafts, the dry static energy, the change in dry static energy can be related to the saturation specific humidity, something that we went through. And so at the end of the day, what you get is that the precipitation is basically the net condensation that you get from upward motion, or actually this also includes the cooling that you get from downward motion. So this is the net condensation minus the fact that you might actually lose some condensates in clouds. Okay, so again, this is the net condensation that you get in your updraft. Some of it will be lost as precipitation at the bottom, and some of it will be detrained as condensates. Okay, does that make sense? Should I say that again? Okay, so this is the net condensation in your cloud, in your updraft, sorry. Net condensation from upward motion, and part of these condensates will fall as precipitation, while part of those condensates will be detrained as clouds and lost. Okay, and that's quite common actually to rephrase this and to say that precipitation is related to the amount of condensation that you get with a precipitation efficiency. Okay, so for a given condensation, depending on how efficient you are at precipitating, for a given condensation you can have more or less precipitation or more or less detrainment in clouds. Yeah? Okay. So for this scaling, let's see what happens when now we increase the temperature. So this is again the scaling. And empirically, I find that the precipitation efficiency doesn't change. Okay, I can't tell you why, but that's what I see empirically. And so the change in precipitation is related to the change in the condensation, which I can split into, I would call it a dynamical term, so the change in the vertical mass flux, and the thermodynamical term, this famous Clausius-Clapeyron, the change in saturation humidity. Okay, so let's see if the scaling works. Obviously, since I'm telling you about it, it should work, and it does, reasonably. So the scaling is in blue. This is again the amplification that we saw going to about 7% per Kelvin. The scaling is in blue, so it does capture the leading order change in the extremes. And note that it works better at the highest end, as you would expect, because I've neglected the terms that could start to be important at lower percentiles. So this is really a scaling for the highest percentiles, because we've neglected a lot of terms. Okay, and so how do the thermodynamic and the dynamic contributions look like? Thermodynamic is in green, and actually for comparison I put the change in water vapor, and they don't match. They don't match. So the thermodynamic is slightly is closer to the change in surface water vapor. Okay, so we'll come back to this, but you can already have a hint from here. See that thermodynamic is not the change in humidity, it's the change in the vertical derivative. And if we say that the vertical mass flux has I don't know, representative values in the mid-troposphere, then you can remove it from the integral, and you get the integral of d dz, and so you get the humidity in the boundary layer at low levels. Yeah? Okay. I'll do this later, but I just wanted to give you the flavor. Okay, so the thermodynamics actually not Clausius-Clapeyron, but closer to the surface humidity change. And the dynamic is smaller, but it's negative. And what consequence does this have for the change in extremes in climate models? If we believe that we can extrapolate those results, it's not a given, but let's say we can, then we see that the amplification of extremes is actually slightly smaller and closer to the surface Clausius-Clapeyron than to the atmospheric Clausius-Clapeyron. Surface Clausius-Clapeyron is not maybe a very, it's not a jargon, it's not something that everybody uses, but I use it as the change in humidity at the surface. Yeah. Oh, this is the global mean. Yes, thank you. This is the mean on the domain. Yeah, because again, we're trying to relate extremes to mean quantities to have some. We're not interested in the last digit, but more like the leading order behavior. Is it the mean water vapor? Is it the mean surface water vapor? It's the scaling, so it's approximate. But yeah, thank you. This is the mean. That's why it's constant. And so if we believe that precipitation extremes will increase with surface Clausius-Clapeyron, not Clausius-Clapeyron, then in terms of values, that's a significant reduction of what we can expect. You're now below 6% per Kelvin. This is one of the other curves that I hadn't discussed earlier. This is the change in humidity at the surface as a function of latitude in percent per Kelvin. So that's good news, actually. So maybe the extremes will not increase as fast as Clausius-Clapeyron would tell us. Yes? Yeah, that's a good question. I will come back to that. It's not obvious. There's no closed theory for vertical velocities in updrafts. There are a few ideas, but yeah. Yeah, so the thing is, you have more moisture, and so for a given domain mean mass flux, if you have some constraint on that, since you're already carrying more moisture, you don't have to go as fast to carry the same amount of mass flux. So you have, yeah. And I'll show some profiles later in the organized case, because it's more interesting. We'll see that. Okay, but so far for disorganized convection, what did we see? So we can't trust parameterized convection. It's all over the place in the tropics for extremes. The increase is actually slightly smaller and similar to surface Clausius-Clapeyron than atmospheric Clausius-Clapeyron. To first order, it's captured by thermodynamics, and the dynamics are slightly negative and play a secondary role. So as I had mentioned that there has been another study that took the other end, and that was actually a study by David, we didn't know, but we were looking at the same thing at the same time. The difference is that we took the angle to have a very large domain, so a somewhat coarse resolution, to allow for some large-scale circulation, because we thought it could be important for extremes. Whereas David decided to take the other end and have a very fine resolution, very small domain. And I tried to make it to scale. This is not even the right scale. It should be smaller, but I couldn't make it smaller with my mouse. But the good news is we find the same thing. It's closer to the surface Clausius-Clapeyron than to Clausius-Clapeyron. Okay, so now is that still true when convection is organized? What's the impact of convective organization? And the reason why I wanted to look at this is, first, as you know, I'm very interested in convective organization. It's a fascinating topic, which is still quite mysterious. But also because there's a paper that suggested that maybe convective organization could yield an amplification greater than Clausius-Clapeyron. So it's kind of an alarming publication. And that's because in their simulation they found that the vertical velocities, the dynamics, were a positive contribution in their simulations. So that would enhance the scaling. Not only did you have a change in the water vapor, but you had a change in the vertical mass flux. Yeah. Yes, we had some mesoscale circulation, but not organization of clouds. So there are some large-scale winds, and you can see that this guy is maybe 50 kilometers in size. But we don't have like aggregation because we have fixed radiation. And we don't have squall lines because the shear is not sufficient. But we can have squall lines, and this is why actually I wanted to have squall lines in the model. And these are figures that you saw, so for the sake of time, I'll go quickly. Just to remind you, this is a top view from the popcorn convection. The top is the atmospheric water vapor integrated vertically, and the bottom is the near surface temperature. When you add what we call the critical shear, you get a squall line which is perpendicular to the wind for reasons that we saw last time. And when you add even further the shear, you get a supercritical shear. Okay, now the questions are very similar. Basically, without the organization, between the solid and the dashed. But I think there's something interesting that I can't not talk about. If you add shear, the precipitation extreme values almost double. And interestingly, if you add critical shear or supercritical shear, doesn't seem to change much. And I have another story for this. So when I wrote the paper, I didn't really worry about this. I mean, I didn't mention that it was interesting, But what I was interested in is really the change with warming. And one of the reviewers said, well, but that makes sense, right? If you increase the shear below critical, you're going to have more and more contribution from the organization. But once you hit the critical point, the skull line is anyway going to orient itself obliquely so that the shear projected is critical. So you would expect a saturation. The reviewer signed, it was Kerry Emanuel, so he deserves the credit. And I did try to have intermediate shear, and he was right. If you do intermediate shear, you do get an amplification which is in between. Okay, so the value is sensitive to the organization. Okay, end of the story, but the thing that I want to study here is the impact of warming for a given degree of organization. Okay, so the difference between solid and dashed. And this is what we get. So again, this is the ratio. Now I've put it in percentage, so it's easier to read, maybe. And by the way, here the warming is only 2 degrees. So a 10% increase is the 5% per Kelvin. Okay, and if you do the ratio, actually you can already see it here. The increase for the black and the green are somewhat similar. For the red, it's a slightly larger increase. And you can recover it when you do the ratio. The increase for the no shear and critical shear are very similar. The only one that stands out is the supercritical shear. But I would say that given the animation of the simulation and how different they are, this is strikingly small. This is almost disappointing. Or I guess we should say we're happy because the extremes do not seem too sensitive to the fact that it's organized or not. But I think this is strikingly small actually as a difference. So there's something very robust. And it's thermodynamics. Whenever you have a first principle, you can expect that things will be more robust. This is an example where that's true. Okay, and again we can compare to the atmospheric humidity or the surface Clausius-Clapeyron. And so if you do that as before without shear, and similarly with critical shear, it's smaller and closer to the surface humidity change than to the mean, the main mean. Now for the supercritical shear, this one can reach above the surface Clausius-Clapeyron. It's still closer to the surface Clausius-Clapeyron though. Okay, and if we decompose this into the thermodynamic and the dynamic, what would you expect? Well, you would expect the thermodynamic to be pretty much the same because the atmospheric humidity changes fully Clausius-Clapeyron. There could be some differences because of the wind, the surface fluxes, latent heat versus sensible, but overall the thermodynamic contribution is the same for all. Sorry, I didn't say what you were looking at. This is the same figure as before. So it's the amplification in the extreme value of precipitation for different percentiles, in the disorganized, critical shear, and supercritical shear. And then this is the scaling. So yeah, we're happy it works again. It does capture the leading order behavior, namely that those two guys are similar and that the supercritical shear is the only one that actually yields a stronger amplification. And the thermodynamic contributions are similar. It's actually somewhat boring. Thermodynamics is always around surface Clausius-Clapeyron. But the dynamic is interesting. And this is the contribution, although small, is the contribution that explains the difference between the 3 behaviors. It is small, as you can see, it's always near 0. Okay, so someone asked, what's the connection with the surface Clausius-Clapeyron? Why? And as we hinted earlier, we can do an ever simpler scaling. So let's start again from our equation, which says that the precipitation, the change in precipitation, is related to the change in condensation. And again, the changes in precipitation efficiency are empirically found to be small. I can't tell you exactly why, but they're small. And so here, what we're going to do is say that this integral can be approximated by maybe the vertical mass flux has a representative value at 500 hectopascals, and then you end up with the integral of ddz, and so there's no humidity at the top, and so you end up with the humidity in the boundary layer. And so a rougher scaling, but again, I'm not after the 10th digit. I want the leading order behavior of the extremes. I'd rather to have something approximate that I understand than something precise that I don't. And so you find that the extreme can be related to the mass flux in the updrafts, in the mid-troposphere, say, and the humidity in the boundary layer, times the precipitation efficiency, hence the proportional. Okay, and if you do this rough scaling, the agreement is, so it's not as good. We would expect that. But you still explain all of the difference in the dynamic, and now it's simpler. It's only the vertical mass flux at 500 hectopascal. So the reason why the supercritical shear or the organization can change the precipitation extreme response is through the dynamics. And it is smaller, but it does yield an amplification which is slightly larger. And we don't have a closed theory, unfortunately, for vertical velocities in updrafts, although there are some ideas. We can discuss them. I'm not planning to talk about it here. But one thing I'd like to mention is the following. So you hear a lot, there were some people arguing in the literature that if you warm the planet, you have more humidity, so you have more latent heat. And so if you take a parcel, goes in an updraft, the latent heat is larger, so it's going to have a larger boost, and it's going to go higher and faster. So we should expect vertical velocities in updraft to be stronger with warming. Now, there's a lot of things that are wrong in this reasoning, but I won't go into that. What I want to show is that here, when you warm, if you actually look at the maximal vertical velocity, it does increase, and the profile slightly shifts upward, as we mentioned. With warming, the profiles shift upward. But what matters for precipitation extremes is not W, it's the mass flux, rho times W. And that actually decreases. And this is why we had a negative contribution from the dynamics. The mass flux per cloud decreases in those two cases of no shear and critical shear. And for the one that stands out, for some reason, the vertical mass flux doesn't change too much. Yeah. That's the downdraft, yeah. Mm-hmm. Yeah. Yeah, so you can try to address that by taking, so the question was, you're looking at this at the time where what falls has been condensing in the earlier times of the cloud, when you had our deep system. So that's why I did hourly averages. The best is 3 hourly average, because then you have the whole life cycle of the cloud. You can do daily, but it's robust. And again, it's better if you do it more accurately, but you can lag it. Yes, you can lag it. Yeah, that's the best actually. If you can lag it, but then it becomes complicated, and the problem is things are moving as well in my case, so then I have to follow the wind, which is why actually I had this weird shear, more important at the surface than higher, because then it didn't move, so it's easier to do correlations or lag studies when it's not moving. Then it gets complicated, but I'm happy actually. I'm happy with this. I mean, aren't you? This works, right? It captures the leading order again. It's but yeah, if you do it more carefully, then you have to average over the life cycle of the cloud, 3 hours, and blah blah blah. You can do it more accurately if you want. Okay, so that's all I say. That's all I say about precipitation extremes. Just to give you the take-home messages, if you have been sleeping a little bit during the talk. So they go similarly. The precipitation extremes increase with warming. That's the first take-home message. They increase, and we expect it from thermodynamics. Now the leading order behavior would be it increases with atmospheric humidity. It's not plain wrong, but you can refine it, I think. And it's closer to the surface Clausius-Clapeyron, which is actually good news because it's a smaller increase. 6% versus 8% per Kelvin. Now the organization, surprisingly, does not have such an impact. There are some subtleties, but to leading order, I would say, despite the very different organizations in the runs, the amplifications are not that different. And again, that's because thermodynamics leads, and thermodynamics is, it doesn't care if it's organized or not. It's a first principle, and so you always get something that's around the surface Clausius-Clapeyron. Now the dependence is non-monotonic. It's more sensitive to supercritical shear with rates that are slightly larger than the surface Clausius-Clapeyron. So this is a higher order correction, if you want. And yeah, so the dynamics play a secondary role. Yeah. That is a great question. So the question is, can we relate those? What can we extrapolate from those idealized studies to the real world? That's a great question and a great transition. I think the leading order thing that's neglected here. Okay, so granted, I'm thinking of the tropics. Okay, so first of all, so the extratropics is another beast. But for the tropics, I think something very important that has been left out is the organization. What I did is take a fixed degree of organization, whatever state of the skull line, critical, supercritical, and then warm. But if your organization changes with warming, you're not going from 300 to 302 here, you're going from black to green. And that is a big jump. So that's one thing that actually worried me after this study, is that and that's why I went into convective organization partly. If convective organization changes with warming, that's a big jump. That's bad news for a lot of people living in the tropics. And in fact, there has been a recent study in this direction showing that you can link recent trends. These are observations. And you can link recent trends of precipitation in the tropics to changes in organized convection. So that is bad news. This is the change in monthly mean precipitation up to 2009. And this is the change from the change of rainfall type going into mesoscale organized convection. And as you can see, they match. The other convective regimes yield a very small change. So yes. Yeah, it's a good question. So if you have land, you have an extra factor, which is, so here I'm assuming that most of the surface flux is under latent form, so it's evaporation. Typically in those runs, the sensible heat flux is at most 10% of the surface flux. So most of it is latent heat. Over land, it's not necessarily true. The bound ratio the ratio between latent and sensible can vary. So I would say this is the aridity effect is probably going to change things. And then orography can also change things because it will force ascent, and you can have a non-monotonic change of vertical velocities with temperature, just because. So we did an observational study that I removed, but it's a region where you have a very strong seasonal cycle, and at a given month, you have very strong updrafts for regional reasons. And you see a change in extremes that just is slaved to that. So you always have the thermodynamic, but again, it's boring. It's very predictable. It's always the same. But the dynamic one is actually quite interesting, and it modulates around this value of Clausius-Clapeyron, the response of extremes. But that was more in mid-latitude. So. Yeah. So the aridity effect can also play a role. We saw that in the observations as well. Okay, so there was a quick overview of one topic of research, which is still not fully understood, but there are some recent results. And the last thing is, why do we care about clouds in terms of climate change? What's their impact? What are the processes at stake? And the outline that I had was climate sensitivity, but Tapio talked about it, so I'm really going to be very fast. And then how do we quantify climate feedbacks? And again, I'll be quite quick on this. I'll mainly concentrate on the cloud feedback processes. But I do want to mention those two, and the reason why I want to mention those two is you've heard that clouds contribute to a large fraction of the uncertainty that we have in the climate sensitivity. And I want to show you why we say that. Okay, so first of all, you probably have seen this. This is the Mauna Loa Observatory in Hawaii, and this is the CO2 increasing. And we've reached above 400 recently, which is larger than anything we've known for actually, you can go back to 800,000 years. And it's been known for a long time that if you add CO2 in the atmosphere from basic physics, it's going to increase the surface temperature. And so I actually added the Wannabe and Weatherworld reference. What? Manabe, sorry. I would change it, but okay, it's an M. I was just looking upside down. So actually, in any summer school that I've been to, you see Charney's face at least 3 times. Okay, and that tells you how important this person was, this character was. And he, as Tapio mentioned, was the first one to actually do a sort of IPCC report. And it is striking, I recommend reading it, it's striking how similar it is to the modern ones. And all he had at that time were studies from simple equilibrium models, single column, radiative convective equilibrium, and actually the first one, so he put all those values together in his report. But to be fair, the value of climate sensitivity, the first estimate was from Manabe and Weatherworld. Not WW, but MW. And so what did he conclude? He concluded that the range would be between 1.5 and 4.5 with a likely value of 3, as Tapio mentioned, and that the key uncertainties were cloud feedbacks, the role of the ocean in carbon and heat uptake, and regional precipitation changes. And these still hold nowadays. No, it matters for societal impact. And the problem is we can say, in the deep tropics and by climatic regimes, but the exact location where the climatic regimes are can vary from model to model. There's lots of uncertainty on exactly where, is it going to be over Les Ouches or over somewhere else. So it's more for societal impact that it matters. Okay, and so the embarrassment is that it hasn't changed very much. This has been mentioned before. These are the various, I haven't updated this plot, I should. But I wanted to just mention, why do we care about equilibrium climate sensitivity? Why do we care about this famous 2 degree or the temperature? Oh, maybe I should remind you. So the equilibrium climate sensitivity is the increase in temperature that we get at equilibrium when we double CO2. So you double CO2, you let the climate do what it has to do to equilibrate, and then you compute the new temperature. Okay, that's just to remind you, that's what we call the equilibrium climate sensitivity. And the reason why we care is that for a lot of models, the response that you get at first approximation is a function of space, a pattern in space, but the amplitude is just scaled by this climate sensitivity. And an example is shown here. This is one model, so the French model. Say the Parisian model, because there's 2 models in France, one in Toulouse and one in Paris. Anyway, one model. And this is one scenario, and this is another more extreme scenario. And this is scaled by this equilibrium climate sensitivity. And as you can see, they are very similar. Okay, so what happens is that this pattern, this is the change in temperature, the pattern of warming is the same, but the amplitude scales with this equilibrium climate sensitivity. Okay, so it's not just an easy shortcut to have one value to explain to politicians that it's warming by blah, but it also has some real implications for the amplitude of the signal with the increased greenhouse gases. So that's in models. In the real world, obviously, you might question because models are imperfect, but that's a hint that maybe it's an important quantity. Okay, so about cloud feedbacks. So why are clouds important? We saw that they cover 60% of the planet, so they have to be important. But actually, their radiative impact is not that trivial. It depends on the cloud type. And so I'll start with the low clouds. Basically, you have to, let's do the Earth energy budget from the top of atmosphere. What happens at the top of the atmosphere? Well, we receive solar shortwave, and because low clouds tend to be thick, thinking of stratus or stratocumulus or shallow cumulus, they reflect a large fraction of the shortwave. Okay, that's the leading order. The long wave effect of low clouds is small. And the reason is they're close to the surface, so their temperature is not super different from the surface beneath. Okay, so their emission in the long wave is pretty much the same as what the space would receive from the surface. So the leading order is the shortwave effect. And that means that clouds are actually, low clouds are actually cooling because of the albedo effect, simply. The high clouds are different, and here by high clouds, I'm omitting the deep cumulonimbus. Maybe I'll just say something quickly about those guys. But I'm thinking of more the thin, cirrus ice clouds that we have in the high atmosphere. And they're very thin, and actually it was nice to see how thin they are. If you remember, if you condense all the cirrus condensate, do you remember what thickness you get? It was 0.1? Yeah, 0.1. Something very, very small. And so it's ridiculously small, but their climatic impact is of leading order importance. And the reason is they're very high and thin, so they don't really bother their incoming shortwave, but they emit from a very, very high altitude, so very, very cold temperature. So the long wave effect is enormous. The thermal emission is very low, and so it's not emitting, it's preventing our planet to emit sufficiently in the long wave. Hence, it's a warming effect. Okay, so the effect of clouds is different whether you talk about low clouds or high clouds. Now for the deep clouds, the cumulonimbus, I didn't put them here, but it's kind of a mixture between those two, and so the radiative impact tends to be neutral. Okay, so in the short wave, it's high, but it's thick enough that it has a high albedo, but it also emits from higher up. So it's both cooling and warming, and in the mean, they pretty much balance. Okay, so in our current climate, what do you think clouds do? Who's winning? The low clouds, or the low cloud cooling, the albedo effect, or the colder emission effect, the blanket effect, if you want? The blanket. Let's vote. Who thinks that the warming blanket wins? Who thinks that the albedo cooling wins? More people for cooling. Yes, the cooling wins. Actually, so clouds are helping us, removing the heat that we receive from the sun. I have to admit, I don't think I would have known on top of my head before I actually researched this. So this is not an easy question. But so here I'm showing the cloud radiative effects in present-day climates for January, February, March. The maps are for January, February, March, but here this is the annual mean values. So first of all, what is the cloud radiative effect? It's the measure of the cloud impact on the energy budget. And the way you do this, so it's a top of atmosphere or tropopause. I'm not going to go into the details, but here you can think of it as top of atmosphere. And here, when it's positive, it means it's a warming. So it's the difference between the radiation with clouds and the radiation without clouds. So removing clouds is just accounting for the clear sky contribution. So if it's positive, it means that you have a warming. So for instance, for shallow clouds, we saw it was mainly the albedo. So the short wave with cloud minus the short wave without cloud will be negative, okay, because the clouds reflect part of it. So that's a cooling, and similarly, it's positive for high clouds. And so in the current climate, you see that in the long wave, the annual mean is about plus 30 watts per meter squared. And it's mainly in the deep tropics, places where you have deep convection as expected. That's where you have those high clouds, which are emitting very little towards space. And in the short wave, notice that the color bar is somewhat weird. So this is only positive values, and this is almost only negative values. The color bar is not the same. Okay, and in the short wave, it's a negative term, so it's a cooling term, and it's mainly in the places where you expect to have shallow clouds. And in the net, that means that the clouds are cooling our planet at a rate of minus 20 watts per meter squared. Now this is a large number, and if you think of the forcing of doubling of CO2, it's 5 times that. So that's partly why we think that clouds could have a very strong impact. If they decided to be a positive feedback for some bad reason, then it could significantly impact this equilibrium climate sensitivity. They have a very strong power over our radiation budget. Yeah. Does that matter? Never thought of that. Let me think. Yeah, it does. Obviously, it does. Yeah. So most of the yeah, you have transport but it's going to impact the transport because the transport is just doing whatever it has to do to redistribute the energy. Yeah. I don't know. Does anyone have anything? Oh, the question was, so it mainly cools in regions where there's no one. Does that matter? Exactly. It would change the circulation because so that would be one impact. Right, yes. You're right. Yeah. This is still minus 30, so it doesn't look very large, but it's true that the largest values are over the Southern Ocean. But yeah, it's still cooling everywhere pretty much. Yeah, good point. Good question. I think this is observations. I forgot. I took this slide from Sandrine Bonny. I believe this is observations because it's present day. Yeah. There were some. Yes. Yes. Yeah. Yeah. So you can imagine that especially in winter, the air will get very cold. The water, if you remember, the water is clever, and so it tends to be warmer, and that will lead to convection. But because it's stable, it's not going to go very deep. So mainly it's the water. Yes. 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 The air is still pretty cold. Yeah. Yeah. Should have the other maps as well. Were there other? Was that? Yeah. I should have the other maps as well. I just shortened the talks. Yeah, that's true. But you can easily find those maps. By the way, you can just download the IPCC report and you'll have all the maps that you want. Okay. So now that was the cloud radiative effect in data in our current climate. Now what's the cloud radiative forcing? Cloud radiative forcing is now how this radiative effect changes when you double CO2 or when you change the climate. And so the key question is obviously how will clouds respond to increased CO2 and how will that feed back on climate? And just here for illustration, I'm showing two climate models and how they respond to these forcings. So you add 1% of CO2 per year. This is the global mean change in temperature. And you can see that they have almost a factor 2 or 3 difference in the value of the temperature that they reach. So this is not a small difference. And you can almost attribute everything to the cloud radiative forcing. Okay, so I'm trying to go towards the fact that the clouds are one of the largest sources of uncertainties in our current predictions. And this is one example where you see it, or one way to look at it. If you look at the cloudiness, it means, so remember the clouds are cooling overall. So if you have less clouds, you expect to receive more and hence to be warmer. And this is what you see. And people have been thinking about this. So this is just one way of looking at it, but clearly there's something more fundamental. Maybe we can have a more mathematical framework to formalize the link between the change in the global mean temperature and the change in cloudiness. And so I want to show you this framework, how we compute the feedback parameters. Okay, so let's go back for that, we have to go back to the top of atmosphere energy balance. We receive short wave from the sun, re-emit a fraction of this, which is the albedo, and then the Earth re-emits in the infrared, whatever it has to do to be in equilibrium. And so the radiative disequilibrium at the top of atmosphere is what we receive minus what we emit. So far, so good. Now what happens when we put CO2 in the atmosphere? We change this balance, and it could be any forcing actually. Let's say we change this balance so that what we receive is more than what we emit, so we have a positive anomaly at the top of the atmosphere. We receive too much. What's going to happen? What's going to happen? Well, the Earth doesn't have much choice. The only thing it can do is go back to equilibrium by increasing this guy. Okay? And so the dependence of outgoing long-wave radiation on temperature, it's the main restoring force. It's actually not exactly the only, but it's the main restoring force to go back to an energy balance. And so you can linearize this if you have a small change, and so it was found that the radiative response is proportional to the global average temperature. And so what does that mean? Let me rewrite this in a slightly different way. The OLR was sigma T emission. I didn't say TE was T emission, the emission temperature of the Earth. And now this emission temperature is a function of the surface temperature, but also of the content of the atmosphere. So if you have more CO2, the emission level goes up, so the temperature goes down, the emission temperature. If you have more water vapor, similarly, the emission level goes up, so the emission temperature goes down. You're higher in the atmosphere. Clouds change things as well. And so let's do a thought experiment where we abruptly increase CO2. Okay, so what happens? We said if you increase CO2, then the emission temperature goes down, and so the outgoing long-wave radiation goes down, and so we are not in balance anymore. So what will the atmosphere do? It will warm until it reaches the new emission temperature that it needs to be in balance. And so in time, what happens is, this is the so-called Planck response, so it's the simple response in sigma TE to the 4. So you have a radiative imbalance, and then the temperature will slowly increase until you reach your equilibrium again. Now let's take, this was just for the Planck response. Now let's imagine that the water vapor increases with surface temperature, and now you all know we have very good physical reasons to believe that's going to be the case. It's pure thermodynamics. So if you take that into account, as the temperature increases, the water vapor increases, and so the emission level actually increases even more, and so you need an even larger warming to balance the top of atmosphere, to close the energy budget. And so the temperature response that you get is even larger. Does that make sense? Yeah? Let's do yet another one to make sure that this makes sense. So now let's assume that the ice is melting as well as the temperature is increasing. What's happening? So you still have your forcing. It's trying to do its Planck response. Water vapor increases. It needs an even larger surface temperature increase to close its energy budget. But its albedo is decreasing. It's returning less and less shortwave to the sun. So it's receiving even more as temperature increases. So you need an even larger temperature increase to reach your new equilibrium. And actually, if you write this mathematically, what you find is that actually this slope here is nothing but the feedback parameter. Okay, and that's the way to quantify the effect of, say, temperature at constant other stuff, the impact of temperature on the radiative imbalance. And similarly, then you can quantify, so you have the impact of CO2, then you have the impact of temperature. So it's nothing more than partial derivatives, but physically it tells you what's the contribution of each different feedback to the equilibrium climate sensitivity. Okay, and so the equilibrium climate sensitivity in that case is simply the instantaneous forcing, so the rate of change, keeping temperature fixed, so just changing CO2, that's your radiative imbalance, divided by the sensitivity, so for a given CO2, how much does the radiative imbalance change as you change the surface temperature? holding CO2 fixed. Okay, so the equilibrium climate sensitivity is simply given by minus F over lambda. Okay, so yeah. Okay, so just to show you, actually these are called Gregory plots, what I showed you, those radiative forcing and then relaxation towards a new equilibrium. This is called Gregory plots, after Gregory. And this is a model simulation of what happens when you double CO2. And you'll see that this conceptual picture is actually very relevant. So here we abruptly increase CO2, and the net top of atmosphere radiative flux increases. I'm sorry. Yeah, it increases instantaneously, and so what happens is that the surface temperature starts to increase because the Earth is trying to emit more to reach a new equilibrium. So it keeps increasing until you reach your new equilibrium, and the top of atmosphere radiative imbalance goes to 0. Okay, so that's the time evolution, and this is the new way of plotting this. Instead of a time evolution, we plot the radiative imbalance as a function of the temperature response. So first you give the kick to your system, the radiative forcing is positive, and then your model, and these are different experiments. This is a 4 times CO2, by the way, not twice CO2, but the idea is the same. The temperature increases and the radiative imbalance decreases until you reach your new equilibrium. Okay, so this is exactly what climate models do. No matter how complicated they are, they have to do this to close their energy budget. Okay, but what that means now, this new way of framing things, is that you can separate the different feedbacks. Okay, so you have the feedback, the Planck feedback, we saw that, and then you have the water vapor, which was adding a little bit of warming, and then you have the cloud feedback, the ice feedback, etc. So that's a nice way to quantify the different feedbacks. Again, so this is more physically. Mathematically, it's just a bunch of partial derivatives holding the others constant. The nice thing is it's really isolating the effect of each individual component of the climate system. Okay, and so I would have liked to go into more detail, but I will have to refer you to this paper. If you're interested, there's more to this. Brian Soden and Isaac Held developed another framework, radiative kernels, which are highly relevant to this, and it's I think it's a very clever tool. So I don't have time to talk about it, but again, if you're interested, come see me at the coffee break. I have some extra, about 30 extra slides to show you on this. Okay, but I'll just show you the results. So if you apply this to climate models and you say, you know, what is the feedback in each of the model? This is what you get. And so you find that the Planck response is a positive feedback, but most importantly, it's the same in all the models. So it's very robust. So that's not leading to uncertainties between models. If you look at the water vapor per slabs rate, yeah, it's customary to add those two because they tend to compensate. But if you add those two, then you see that there is some variation, but it's still quite robust between models. The surface albedo feedback, it's smaller, and it's somewhat robust between models. But now the cloud feedback is all over the place. And this is the type of plots that led us to say that cloud feedback is one of the largest uncertainties in climate models. Now I want to add a word of caution to this. It is the largest source of uncertainty in climate models based on climate models. So it's not accounting for things that climate models do not do right or are missing. And I'm thinking of convective organization, obviously, now you know. But based on climate models, from what we can diagnose, we know that this is at least one target we should aim at. We should be able to reduce this uncertainty. It's mainly ice, yes. So this is 2008. I don't think all the IPCC models had aerosol forcing at that time. I'm not too sure. But yeah, I think the aerosol was not yet prescribed in all the models at that time. Now they do have some aerosol constraints. But yeah, yeah. Exactly, just the sigma T to the 4. Yeah. And then the others just change the emission level. So it means that when you relate to the surface, you have to do more or less warming at the surface to get the same emission temperature. Yeah. So all the others are related to a change in emission level. Not all the others, not the ice, but yeah, most of the others. Yeah. Mhm. Yeah. Okay. So the question is, you don't resolve organization in climate models, at least in the tropics. And so if you put a cloud resolving model, what do you get? Does it actually significantly change the cloud feedback? So actually, um, so the answer is, for deep convection, the cloud feedback does change. And I'll go into the processes. That's the last thing I want to talk about. And that's because the cloud fraction changes. And if you remember with aggregation, for instance, the clouds tend to aggregate, and the aerial cover of clouds decreases. So you do have a strong cloud feedback associated with organization. Now, from the models, actually, this uncertainty is mainly from shallow clouds. And it's related to the change in cloud cover in the subtropics and at polar latitudes. Yeah, I don't know if they had the coupled ocean in those simulations. I'm not sure. Probably. That's a good point. Yeah, I haven't looked at the ocean at all, but it's true. And actually, as we discussed yesterday evening, the ocean has taken. So along the way here, as the Earth is warming, we're not in equilibrium, and we are receiving actually currently more than we're emitting. And of the excess radiation, do you know how much the ocean has taken of the excess radiation we've received? Those of you who were here yesterday night can't talk, can't answer. 93%. More than 90% went into the ocean. So the ocean has been very nice to us so far. But then it's been expanding and warming and acidificating, something like this. Anyway, processes. Let's talk about processes, because it's always nice to see motivations, but if you don't understand things, what's the point? So let's talk about, actually, I mainly want to talk about what we don't understand, because I think that's interesting, and it's probably good for you to know. A lot of what I'll talk about is in this paper. It's a really nice paper. I recommend it. Okay, so the question is, now we know the cloud feedback is a large uncertainty. Let's try to narrow it down and see where this uncertainty comes from. So this is the cloud, this is the cloud feedback, the net in red, and then you have the long wave, in black, obviously, the long wave in red and the short wave in blue, and then you can split it into different groups. Okay, so is this feedback uncertainty related to the height of the clouds? And as we've mentioned a couple times, actually the largest uncertainty in the net comes from the low clouds. And so consistently, it's mainly short wave. We saw that low clouds were mainly having an impact in the short wave, not so much in the long wave, because their temperature is close to the surface. The middle cloud, yeah. Yes, exactly. So the remark was that if you look separately long wave, short wave, the high clouds have a large uncertainty. Yes, that's a good point. The reason is that again, for a deep high cloud, you do have a strong albedo, so a strong shortwave cooling, but you also have a strong long wave warming because you're emitting at a much colder temperature than the surface. So you have a net warming effect. And for high clouds, that tends to compensate. So that means that the distribution of high clouds is probably very different in the different models, but in terms of radiation, it doesn't matter. Again, based on how climate models do high clouds. Not exactly, no. no. We're still lacking a very good, yeah, theoretical reason for that. There are some ideas, but okay. So it's mainly from low-level clouds, and then you can split it differently and look at what happens if you look in terms of amount, altitude, and optical depth. And in a warmer climate, we see that there are fewer clouds, which is a positive feedback. Remember that clouds are helping us. They are removing, they're on the net, they're cooling. And so if you have less clouds, that's a positive feedback. It's mainly in the short wave, consistent with the low cloud response. There are higher clouds, which tends to be a positive feedback, and I'll come back to this. Yeah, in terms of cloud type. That's mainly a high cloud. And then their optical depth is thicker, so it's a negative feedback. Okay, so why does the optical depth increase? It's mainly actually at high latitudes, poleward of about 40 degrees. And so the negative feedback mainly arises from the exotropics, and it's likely due to changes in phase or the total water content. Okay, now the higher clouds. So I want to spend some time talking about fat and then dismissing fat as fit, or giving you a somewhat of an overview of where we are, and I was going to say what we understand. I should say what we understood and now think we don't understand anymore. Okay, so again, this is the radiative convective equilibrium, and there's this argument that the height of the clouds, which is what matters for high clouds, because it's related to the temperature at which they emit. And it's been argued that the temperature of the high clouds should not change with warming. Okay, so even if you warm, the clouds will go at another altitude so that their temperature remains the same. And the argument, and I should say, so this is an SST, this is a CRM study with this model where they increased the sea surface temperature, and they find that first the profiles extend upward. We said that the profiles stretched. We've seen that before. And it stretches so that the temperature of the high clouds remains the same. And the argument goes like this. If you're in radiative convective equilibrium, you can see it as a two-box model. So you have the cloudy region and the environment. And in clear skies, the radiative cooling has to be balanced by the adiabatic heating. Okay, if we go back to our dry static favorite equation, dry static equation, what do you have? You have the change of dry static energy is related to the diabatic forcing. So you have the radiative cooling, and you have the latent heat. But in the environment, there's no latent heat. There's no condensation. So the only balance is between the radiative cooling and the adiabatic warming. Similarly, actually, in the cloud, the main balance, this is a side note, but the main balance is between the adiabatic cooling and the latent heating. And you can actually neglect radiative cooling because the latent heat is much larger. Okay, so these are your two balances depending on whether you're in the cloud or in the environment. Okay, so but back to this. So you have that W is related to the radiative cooling rate. And now if you look at the radiative cooling rate, it decreases very sharply, around 200 hectopascals in that case. And if it decreases very sharply, W has to decrease very sharply because it's directly related to Q, assuming that the stratification doesn't change too much. Okay. And so if W decreases, we have a continuity equation. It means that you must have convergence in the environment, and hence, for mass conservation, divergence outside of the moist region. And so basically, the location of the high clouds is wherever you have this very strong change in radiative cooling. So this has been called the FAT hypothesis, fixed anvil temperature. And I did spend some time looking for FAT and fit illustrations. So we saw that this is a cloud fraction as height. Now if instead you plot it versus temperature, what they found in their simulations is that there's a very good agreement. But now this has been revisited over a wider range of SSTs by Jacob in the room. And over, I guess, a wider range of SSTs and experiments, this does not hold anymore. You do have a change in the anvil temperature. And that's because the idea that the cloud detrainment is determined by the environment is suspicious. Maybe it is better to think of the location where the clouds are detrained as being set by the convective region. And basically what happens is that the detrainment is not only in one place, it's everywhere, but what matters is how quickly the clouds dissipate. Is that right? Okay, good. Okay, and so it turns out that the temperature of the high clouds can change. They actually can warm, but it's still less than the surface warming, which is what matters for the cloud feedback. Okay, so what does that mean? It means that quantitatively we're not sure, but qualitatively, as long as the top of the clouds does not warm as much as the surface, it's a positive feedback. All right, because for a given temperature at the surface warming, you need to emit more, and the clouds do not warm sufficiently. So they don't warm in step with the surface. So that's positive cloud feedback. And so the last thing is the cloud amount, and that's probably the largest uncertainty. So for the low-level clouds, it is observed that the low-level cloud amount decreases for a reason that we don't fully understand. So we know that low-level clouds, in current climate, the low cloud fraction is closely related to the low tropospheric stability. And so after yesterday's talk by Shi Yu, I asked her, is it the same for polar clouds? And she said yes. So all this is for subtropical, but actually it's also true for polar clouds. So the amount of clouds is related to the lower tropospheric stability. The lower tropospheric stability is supposed to increase in a warmer climate, and yet the cloud fraction decreases. So there's something we don't understand here. And so there are ideas, and I don't have time to go into detail, so I'll just give you the two references. There's this paper, which basically argues that it has to do with the change in surface fluxes. And this paper, which somewhat slightly different, it's arguing that why do you have such a spread? And it's because once you have a low cloud, there's a positive feedback. The low cloud generates radiative cooling at its top, and that will enhance low cloud formation and convection. And so that's why climate models are either positive or negative, and there's such a wide spread, because as soon as you have a small difference, it's amplified by this feedback. So I think that's an interesting idea. Okay, and for the high clouds, obviously that's a big question. What determines the high cloud fraction? Note that neither fat nor feet tell you anything about the cloud fraction. It's only the cloud height. And then, as you all know now, organization or aggregation can change the cloud fraction, and this is still a big unknown that you should all be working on. Okay, so this is the end. Clouds in a changing climate, many remaining questions. What controls the low cloud fraction, the high cloud fraction, the mesoscale organization of low clouds and high clouds? Fat or a fit? Why? And then what impacts the hydrological cycle, more for societal impacts, both the extreme precipitation and the updraft velocities. And so with this, I'll thank you very much for your attention. It's been a pleasure to lecture here. And I just want to end with my little attempt to try to do some time-lapse here, and I hope to do more this afternoon. These are the lenticular clouds that we saw, and this is a time-lapse. The problem is that this is just been trying a few frequencies outside of my window, but there's too much wind, so you basically just see things moving, but it's hard to see a deep cloud forming, so I'll keep trying. If I see something nice, I'll let you know. Thank you.